Good morning to Dr. Chen and my fellow friends. Today we are going to present our SCL assignment part A. My name is Nurbazila Binti Haide. My metric number is 224596.
My name is Nur Atira. My metric number is 222432.
My name is Lydia Fakia binti Fazli. My metric number is 223154.
My name is Putri Farisha binti Ahmad Afrin and my matrix number is 223385. To start off, we need to define and explain the space, metric, and completeness. So definition of L2 is the space L2 consists of all infinite sequences x equals to x1, x2, x3, and to infinity of real numbers where the sum of square converges to a summation of k equals to 1 to infinity equals to xk to the power of 2 less than infinity. Meanwhile, for definition of the metric law, for two sequences x equals to xk and y equals to yk in L2 defined with rho xy square root of summation of k equals to 1 towards rho x1 mistake. So firstly, we have to define and explain the space, metric, and completeness. So the definition of L to power L2 is the space L2 consists of all infinite sequences x equals to x1, x2, x3 until infinity of real numbers where the sum of square converges to summation infinity k equals to 1 xk to the power of 2 less than infinity. So the definition of the metric law for two sequence x equals to xk and y equals to yk in L2, we can define with rho xy is square root of summation infinity k equals to 1 in modulus xk minus xk minus yk square. It satisfies four axioms, which is non-negativity, identity, symmetry, and triangle inequality. So firstly, we have non-negativity. So this, because of it is square root, it's the rho xy is always equals to more than equal to 0. Meanwhile, for the identity is rho xy equals to 0. We can also say that x equals to y. For the third axiom, which is symmetry, we could say that rho xy equals to rho yx because xk minus yk to the power of 2 equals with yk minus xk to the power of 2. This is because it is symmetry. So last but not least is triangle inequality. So rho xz is always less than equals to rho xy plus rho yz because we apply Minkowski inequality to this sequence. So because of all of these four axioms, we could see that L2 rho satisfy all metric space axiom. So for the step 1, we have to talk about cosequence L2 and rho. For example, this is some of the arbitrary sequence of L2. So take xn1, xn2 until xnn. We could say, for example, xn1 to infinity and equals to 1. We could say that x11, x11, x21, x31. More example is n to the power of xn to the power of 2 is x1 to the power of 2, x2 to the power of 2, and x3 to the power of 2. We could also see that xn to the power of n is x1n, x2n, and x3n, and more. So from previous note, it is known that norm defined on L2 rho is defined as square root of summation infinity k equals to 1 xk to the power of 2. For any xn, xm in element to L2, we have rho xm equals to square root of summation infinity k equals to 1 xk to the power of n minus with xk to the power of m square root, where n, m equals to 1, 2, 3, and more. Since xn, xm are cosequence, then there exists n in element in Z class such that rho xn, xm less than epsilon whenever mn more than equals to 0. Rho xn, xm equals to norm xn minus xm less than epsilon 2 whenever m and n is more than equals to n. So this is for the step 1. Moving on to my next member.
Okay, so I'm going to explain the step 2, where we want to prove that the limit is in the space L2. Since xn is Cauchy in L2, so there exists some constant a greater than 0, such that for all n where xn equals to x1, x2, x3 up to xn, where the L2 is defined by summation of xk power of n squared, square root less than a, and then we take the square for both sides, and then we get the summation of xk power of n squared less than a squared. Because sequence xn is Cauchy in L2, then every xk power of n is Cauchy in real number. Then it also converges into limit xk where n goes to infinity, and therefore this defines a new sequence where x bar equals to xk, where k is equals to 1 to infinity. Then we want to prove summation of xk squared less than infinity, where the infinity means it is finite and it is bounded above. And then we take the inequality where we know x bar is equals to xk equals to xk minus xk power of n plus xk power of n. And then we use the identity over here, where the identity is a plus b squared less than 2a squared plus 2b squared. Then we apply to our inequality. So xk squared less than 2 xk minus xk power of n squared plus 2 xk power of n squared. And then we take the summation for both sides, where summation is from k equals to 1 to infinity. And therefore, we know that xk minus x and k, which is the x bar minus xn squared less than epsilon. Therefore, we got the 2 epsilon. And then we know that the xn now is less than some a squared, just like above. And therefore, we got the total sum square of x squared is less than infinity, where it is mean that it is finite and it is bounded above. Therefore, this shows that x bar is in L2. That's all for me.
So next, for step 3, we want to show space L2 is complete. So we recall back definition 6.4.1, which the metric space is complete if every Cauchy sequence Xn is L2 in L2 converges to X in L2. This is what we want to aim. Thus, I will explain my working. So first of all, we need to do norm Xn minus Xm equal summation infinity k equal 1 Sn minus Xm to the power 2 to the power 1.2 less than epsilon whenever nm greater than n. Sorry. So next, we need to square both sides. So from here, the answer will be summation Xn minus Sm to the power n to the power 2 less than epsilon to the power 2. Next, we square root both sides. From here, we square root both sides. Then, the last answer we will get summation k equal 1 Xn minus Xm less than epsilon. This here we show it converge. So from before this step 2, we know that x and k converge to xk in real number. Then limit m approaches to infinity, xmk equal xk implies to norm xn minus x bar less than epsilon for n
greater than n. So thus x1, x2, x3 is xn are all Cauchy sequence in L2 that converge to x bar in L2 such that norm xn equal to summation infinity k equal 1 xn k power of 2 power of 1 over 2. That's all.
So now I would like to recap the key steps of the proof and explain the significance of completeness, especially in the context of the space L2. So in this proof, actually we aim to show that the space L2, which is the space of all real sequences whose squares are summable, is complete. So that is, recall back the definition, which is that is every Cauchy sequence in L2 must converge to a limit that also lies in L2. So in step 1, we started by taking an arbitrary Cauchy sequence xn in L2. So each term of this sequence is itself a sequence of real numbers. And since the sequence is Cauchy in the L2 norm, we know that for each fixed coordinate n, the real sequence is also Cauchy in real number. And because real number is a complete space, each of these sequences converges to some limit xk. So this allows us to define a new sequence, which will be our, which we construct it as a limit. So in step 2, we prove that the limit sequence actually belongs to L2, meaning that the sum of the squares of its entries is finite. We must show that it is finite. And to do this, we use the triangle inequality here. To estimate and compare the xk2 with xkn power of 2 and show that the infinite sum remains bounded. So when it is bounded, which confirms that x lies in L2. So this here show that it is bounded. It is the meaning here less than infinity, not like means that it is not approached to infinity. Next, in step 3, we then prove that we then want to prove that the original sequence xn converges to the limit x in the L2. So this means the distance between xn and x measured by the L2 metric goes to 0 as n approach the infinity. So this final step ensures that the Cauchy sequence truly converge to a point inside the space. So this is what we want to show in step 3. So next I will go about the why completeness is important. So why is all of this importance? So completeness is a key property in mathematical analysis. So it ensures that the space is closed under limits of Cauchy sequences, or in other words, that we can safely take limits without leaving the space. And for the space L2, this property is especially meaningful because L2 is a Hilbert space. So which means it has an inner product structure that allows us to do geometric style reasoning in infinite dimensions, like working with orthogonality, projections, and series expansions. So without completeness, many core theorems in functional analysis, such as the projection theorem, Parseval's identity, and the convergence of Fourier series, will not hold or could fail unpredictably. So I think also completeness guarantees that analytical processes like approximation, optimization, and solving equations via interactive methods will behave consistently within the space. So to conclude, the completeness of L2 ensures that this space is stable, well-behaved, and reliable for many advanced applications in both pure and applied mathematics. And that is why this result is not only fundamental, but also very powerful. So that's all from us. Thank you.